Yeah, hi everyone, my name is Sayamshi, and now I'm going to explain about the C store, a column-oriented database management system. So, and here is the outline of the PPT I have prepared. In the PPT, we have introduction, the architecture and features of the C store, that is the columnar database, the problem definition, what is the problem we are facing, research challenges we are facing, and the limitations, the proposed approach to overcome the issue mentioned here, and the validation, the conclusion. So let's say about the introduction. The columnar storage is used to store the data in column rather than rows, and it is responsible for speeding up the time required to return a particular query. So it is responsible for greatly improving the disk input output performance. And also it is helpful in data analytics and data warehousing. The major motive of columnar database is to effectively read and write data. And some of the examples are Mount Database, Apache Cassandra, and SAP HANA, and Amazon Redshift, etc. So by using column store design, database management system can avoid unnecessary attributes into memory by simply reading the values of the columns needed to process a specific query. So it offers a significant performance to boost in warehouse applications where common search include aggregates over a huge number of data items. Like it uses the aggregate operands, and a column store can save disk bandwidth in two ways. Like just now I said, it is used for saving the disk input output performances. So let's see how can it save. Like the first way is to code the data elements into more compact format, and the second one is the values should be stored in dense packed. And we all know that the commercial relational database database management systems stores the tuples of tabular data as well as B-tree indexes of table attributes. But as now I said, the C store physically stores a set of columns, only columns, not rows. So each of which is sorted by some attributes. And they are also sorted by some attributes which are referred to as projections. And some of the columns may exist in multiple projections. So here's architecture of the columnar database. It's the writable store WS, which is referred to as WS, and is a tuple mover. Is a read optimized store. This is the architecture of the columnar database. And this is a small writable storage component at the top level designed to support high performance for insert and update, and a much larger component known as read optimized store, referred as RS, which can support a very large amount of data. So it can support a very large amount of data, huge amount of data. And read optimized store, as the name suggests, it is optimized for reading and only supports a very limited form of insert, namely batch movement of records from writable store to read optimized store. So insert routed to WS, which is known as writable store, and whereas deletes must be marked in RS, read optimized store, for later removed by tuple mover. It is removed by using the tuple mover here. So insert and deletes are used for implementing the updates for this one. And now let's look at the next one. And the features. Okay, it comes to the features, the hybrid architecture that combines WS component optimized for frequent insert and update with an RS component optimized for query performance. So the table elements are overlapped projections in different orders. So the most advantageous projections can be used to solve a query. So the main feature is like it uses most advantageous projections to solve a particular query. And as there are only columns, that are heavily compressed using one of the several coding schemes. And now a column-oriented optimizer and executor with primitive that differs from those in row-oriented system. Increased availability and performance via case safety with a sufficient number of overlapping projections. The use of snapshot isolation to avoid 2PC and query locking. These are the features and just now we discussed. And the next one is the problem definition. Let's see about what are the problem like we're going to solve or resolve. Like we are going to find the answer for. So the paper addresses like the issue of supporting both OLTP style transactions and analytics or ad hoc queries in a single database system in an efficient manner. So OLTP is the online transaction process. Some of the online transaction process are order processing systems, system retail sales, banking transactions, and airline reservations, etc. So many existing systems are optimized for just one, but not the other. Like it cannot work both at the same time. So most commercial database management systems, according to the others, are optimized for OLTP workloads and frequent writes, whereas data warehouses and other analytical systems are optimized for analytics and reads. Now, the goal is to create a system that can excel both at the same time. So here the author emphasizes that a key issue is the tension between efficiently updating data structures to support transactions and optimizing for analytical queries. Existing solutions of different concentrate on one or the other. So scaling out across many nodes or servers as would be required in large data warehouses is another key issue raised. So most OLTP databases are not concerned with distributed systems. And so let's look at research. So in practical, many businesses have separate databases for OLTP analytics, which adds complexity overhead to data management and integration. So as we can see, like there are a lot of people now and a huge amount of data is generated day by day. Sorry, daily. So we need to organize the data. So we need to find some methods. So as the data volume grow larger, having separate systems become increasingly impractical due to data duplication. So as there is huge amount of data, the data duplication may be possible. So some of the synchronous issues as well, and etc. So the real-time analytics is becoming more popular. Businesses want to analyze data as soon as it arrives, rather than waiting for a particular time period of time to process in batch data warehouses. So this necessitates the use of a system capable of both OLT and analytics. So we need to find a system that's comprised of both OLT and analytics, which works for both of them at the same time. So it is a difficult technical challenge that involves storage layout, indexing, querying, transactions, and so on. Solving it can help advance database technology. So let's look at some of the challenges that we're going to face. So trade-off in storage layout, row-oriented storage is better for OLTP. So the row-oriented storage is nothing but which stores the data in the form of rows, only particular rows. Yeah. So while column-oriented storage is better for analytics, and the row-oriented storage is better for OLTP, while the column-oriented storage is better for analytics. So it is difficult to find a single layout that works for both of them, for both the row-oriented storage and the column-oriented one. So another challenge is indexing trade-off. Indexes are designed to accelerate lookups and transactions may differ from those designed for large scans and aggregates. And the last one is query optimization. So it is difficult to write a query and execution engine that can effectively handle both OLT lookups and complex analytic queries. Some of the challenges are concurrency control, data loading, and hardware utilization. So concurrency control is mostly occurs in transactional consistency mechanisms such as locking can limit parallelism for analytical queries, and a huge amount of data is impossible, like not impossible, but it's quite difficult to load for both workloads. Hardware utilizations. So optimizing the use of modern hardware such as large main memory, multiple cores, SSDs, and so on for a variety of workloads is difficult. So distributed architecture, it is difficult to scale out to many nodes in a cluster while keeping both workloads efficient. Let's look at the limitations of a project. So row-oriented OLTP databases. The row-oriented OLTP databases stores the data in the form of only rows. So on disk, the data is stored in the rows with all the columns were given row stored together, and this optimizes for quick row lookups and updates. It is helpful for quick row lookups. So, however, scanning entire columns for analytic queries result in poor cache utilization because you must load entire row. Yeah. So if you are looking for a particular number of particular number of rows, but you need to load the entire rows for all that. So you need to load the entire rows. You must need to load the entire rows for that, which uses a lot of disk space. And analytical queries such as aggregations frequently require only subset of columns, whereas row stores must load entire rows from disk. So these operations require subsets of columns, but the row-oriented OLTP database is stored in the form of rows, so it must load entire rows from the disk, which is both time-consuming and data-consuming. So the column-oriented data warehouses stores the data in the form of columns. So there are many columns are available, and you can easily take the subsets from them. It's easy for drawing out the subsets from the particular number of columns. Like we can take whatever the data required, only the data required for our. However, row-oriented updates and transactions necessitate the extraction of data from multiple columns, resulting in poor write performance when compared to row stores. So column stores are not only designed for low latency points lookups. So we can say the data warehousing, OLTP data, these are the OLTP databases. So we can extract and transform and load from data from these databases to OLTP data warehouse. So let's look at the proposed approach. So in previous, there is no system has solved the entire problem of optimizing both OLTP and analytical workloads at the same time. Like existing solutions are either like they work at either OLTP or analytical, but they don't work for both at the same time. So hybrid transaction and analytical processing will be available in 2023 to handle mixed workloads. The paper introduces new techniques for providing excellent analytics over a primarily column-oriented architecture while allowing transactions through a secondary row-oriented storage. So we can see there's a lot of people working on some data. The data is stored in the database and which can be retrieved later from the database through some queries. So proposes a new hybrid database architecture with distinct transactional and analytical components to achieve excellent performance on both OLTP and analytic workloads at the same time. So this novel approaches that has not been used in the previous work, like it's the first time. So it may be tricky and quite complex as well. So it provides a column-oriented analytical store that is optimized for scans and aggregates via columnar storage, dense packing, and compression. So previous column stores are extended. It introduces snapshots isolation for analytical queries to avoid locking overhead, and multi-version concurrency control theory is extended. So it displays a tuple mover designed for bulk data transfer from row to column store, and this mechanism as well as the integration of a disparate store is novel. So this is the system design for our proposed system. You can see the database is here and the applications changed in snapshot. The dimension of 30 is here, which can be formed into batch later by using, then later it is stored in the database data warehouse. And coming to the validation, the columnar store of two commercial database systems. The one is row-oriented and one is column-oriented. Experimental measurements with benchmarks is validation methodology. So they employ a streamlined TPC-H benchmark with a subset of tables and queries that representative of analytical workloads. This is a decision support benchmark used in the history. The query latencies for the same analytic queries runs on all three systems were measured. This directly measures the performance of analytics. The experiment manages storage space across systems and fine-tunes the schema and layout of each system. It runs two experiments, one in which the space is limited and the one in which the other systems can use more space. So uses an established benchmark and metrics that are directly measured to the goal analytical performance. By schema tuning and controlling space, performance comparisons are made as fair as possible. So let's look at this table. Like we have queries and we have C store, row store, and column store. So this is C store, and it can work at the for row store and column store at the same time. And coming to the conclusion, and the given one has presented the design for C store, a radical departure for current DBMS architecture. It is aimed at the read mostly DBMS market and opposed to current commercial systems. C-Store's innovative contributions include a column store representation with an associated query execution engine, just now I showed, and the hybrid architecture that supports column store transactions. We have looked at the transactions, architecture as well, and a focus on reducing disk store costs by coding data values and dense packing the data. A data model comprised of overlapping table projections as opposed to the standard pair of tables, secondary indexes, and projections. An optimized design for assured nothing machine environment. So distribute data transactions that do not require a redo lock or a two-phase commit. Quick snapshot isolation. So here are some of the references I have taken for this presentation. Thank you so much.